Okay, I will go to here. Yeah. So as you see, this is the current developed direct air captured solvents. I listed the basic performance, including the CO2 capacity and the kinetics. We use half time to describe the kinetics. And the dashed line below the dashed line are the two moisture swing of the solvent developed by Columbia University when I worked at Columbia University as a postdoctor, and the current developed the solvent at our university of China, and the doors above the dashed lines are the solvents based on the temperature swing of the sorption. And you will see that it seems the temperature swing of the sorption has a higher capacity, but we found that the reported temperature swing capacities most of them are based on the powder samples, and the two moisture swing of the solvents actually are the shaped of the solvent, which means it can be used directly in the reactor. And the other very important parameter is the half time. If we have a shorter half time, it means we can finish the cycle very quickly. And you see that for the moisture swing and the temperature swing, the sorption, it seems they both can finish the sorption most of the half time in less than 10 minutes. So that's a great advance, yeah, in the material development. And we all know that today the reason why we get together because we want to use the direct air capture, and of course we can use the temperature swing of the sorption or moisture swing of the sorption for pure CO2 or some low concentration CO2. That's one of the characters of the moisture swing of the sorption. If we just use water without heat or electricity, you will get 1 to 5% of CO2. That is limited by the thermodynamics. But we can also get pure CO2 with additional temperature, high temperature heat, or electricity. So with the pure CO2, you can use the CO2 for materials or chemicals like mineralization or geological storage. Or you can also use the low concentrated CO2 for the greenhouse, for the farmers. They like that very much. And this is a mechanism of the moisture swing. Look at the right corner of the slice. You will see this is a functional group of the polymer. We use a polymer, and it has these alkaline groups. So the alkaline groups can capture the CO2 and form the bicarbonate. The bicarbonate will react with water to release the CO2 out and return back to these carbonate ions. And if we dry this material, we release the water, we dry the material, you can go back to the origin state. So that is the mechanism of moisture swing. And so you can see that for the moisture swing, this is the adsorption isotherms of the isotherms of the material, and at different temperatures. So we have the moisture swing can tolerate relatively high humidity, like 60% of humidity. And of course, it's called moisture swing. So you can also say that the disadvantage is it cannot work at very high, like over 80% of relative humidity, because we use that high moisture relative humidity to dissolve the CO2. And another advantage is the high stability of the functional group. You can see that these are the polymers, and the functional groups are linked very strongly to the backbone, and the material is not easy to be degraded. It's not like the amine-based temperature swing adsorbent. And the another advantage is the regeneration and a mild condition. That means it doesn't need high temperature heat like over 100 degree or 200 degree, and it doesn't need electricity neither. Yeah. And so you can compare the regeneration energy. And of course, we can match the direct air capture moisture swing with some biological conversion like algae or agriculture, because the concentration match. You see, at 1% of CO2 or 3% of CO2, the algae can get the very high biomass density compared to atmosphere's the CO2 environment. And so how the moisture swing adsorption works. This is a basic operation. And you can also find these pictures from Klaus Lackner. We use this kind of material to capture the CO2 in the ambient air. And then when it is saturated, you spray water and the CO2 will be released out, and then you will dry the solvent again to finish a cycle. And of course, you can have some additional devices to storage the CO2. Yeah. And the other question I found from you is that whether we can get pure CO2, because the moisture swing, they said it generally get 1 to 5% of CO2 from the regeneration process. And actually, of course, we can get pure CO2 with an additional operation. Yeah, we call it moisture temperature swing process. Oh, where is yeah. You can see that we can use the kind of salt material to absorb the CO2 released from the traditional moisture swing process. And then we use some low temperature heat, like 19 to 100 degree, to release the CO2. And you will see that I calculate the energy would be large, like 5 gigajoule per ton of CO2, but that is comparable with the flue gas capture from the power plant. So for the moisture swing, you will see that for the traditional process, we need electricity. We need electricity for pumping the air into the reactor. And if we need a pure CO2, we need additional heat, like 5 gigajoule per ton of CO2 to get pure CO2. And then you need additional electricity to compress the CO2 to liquid. So you can compare the energy consumption with the temperature swing adsorption based on the amine-based solvents. You will see that the electricity compression is the same, but the TSA need more heat and more heat to finish the regeneration. So it will reduce a great difference between the total operational cost. And the reason why we need less heat is because that they use the solvent to finish the temperature swing process, but we use the salt solvent to finish the temperature swing process. And during the temperature swing process, you need to heat the solvent to over 100 degree. And if you use solvent, you can do the heat exchange easily, right? You can do the heat exchange between the cold solvent and the heat solvent. But if you use the solid solvent to finish the temperature swing, you can imagine that it is very difficult to recover the heat from the solid material. So that is why they cannot recover their heat and will reduce will result in the very high heat requirement. And so that
What's
is
the solvent you're using there?
There you go.
yeah, it's we are trying different kind of salt solvents, alkaline salt solvents, yeah, which can just like the carbon engineering, they use a very strong alkaline solvent like calcium hydroxide, yeah, other kind of, and to capture the CO2, and the energy consumption actually is not as high as 5 gigajoule, maybe 4 gigajoule per ton, and that is the same level of the flue gas capture. And of course, you can use the sodium carbonate. This is the weak acid, and but you can, it is durable for the moisture temperature swing process. Yeah, just just to increase the partial pressure of the CO2 to a higher level. We don't need very strong alkaline. We already used the moisture swing to capture the CO2 from the air. We just need a second stage to further increase the partial pressure of the CO2. Okay.
And you can still do that at a much lower temperature than, say, Carbon Engineer's full aqueous
Oh
solution.
yeah, because the concentration from the regeneration moisture swing process is already very close to the flue gas. For example, the flue gas from the natural gas power plant is about 4 to 6%. The CO2 concentration from natural gas combustion, yeah, it's from 4 to 6%, and that is in the same level with CO2 from the traditional moisture swing process. So that's the reason why we can use similar solvent as a flue gas capture. Yeah, we have a lot of choices. Yeah.
Yeah. And then I just had a question on your
Yeah.
previous slide in terms of the physical, the one before this. Yeah,
This
so
one?
when you're actually doing the drying part, I wasn't quite clear from some of the papers if that's actively heating it to drying it, or that's just allowing atmospheric evaporation, or kind of how that part worked.
That's a very good question. Generally, if the relative humidity is very low, you can dry it in the atmosphere, like you're drying the clothes in the yard.
Okay, that makes sense.
Yeah. Yeah. And this is a cost estimation for the moisture swing process. And the two parts below is from the 1, 2, 3, 4. The 4 parts below is from the capital cost. The solvent, the cost of solvent dominates the capital. Yeah, and the other two from the operational cost. And you can see that the electricity for pump dominates the operational cost. And this is just the traditional moisture swing process. And we can also do the regeneration at normal temperature or mild high temperature like 45 degrees. But you can get, you see a low capital cost at 45 degrees because you increase the CO2, the partial pressure of the CO2 during the regeneration process. And as we calculated, if you want to pure CO2, just applies about $50 for per ton of CO2. So that is the cost estimation for the moisture swing or moisture temperature swing process. Yeah, and you also asked the ability for scaling. And you see this is a 3-ton CO2 small system we built, let me think, about 5 years ago. And this one is the 10-ton CO2 module we built last year for a greenhouse for farmer. And you see, actually, this is about 3 times larger than the 3-ton CO2. We have we can use different units, 1, 2, 3, 4, and this is a berry. I tried berry this month. Yeah, it's delicious. Yeah, it's the berry season, strawberry. Yeah, they got berry. They produced the berry this last month and this month. So with the many of these units, the system can be easily be scaled. Yeah. So that is the reason why we like the moisture swing. Yeah, I think this is just the final the last two slides shows what we are doing to develop the material. Like for the higher kinetics, we need to further increase the higher kinetics, and also we need to adjust the hydrophobicity of the material. Because you just asked whether we can how we can dry the material. And of course, we hope to dry the material in the atmosphere because it will save a lot of energy. But we also found that if the relative humidity in the air is high, it will cost a lot of time, like 2 hours or even 4 hours to dry the solvent. Then we are trying to use the material with more hydrophobicity, yeah, to decrease the drying process. So that is the brief introduction of the moisture swing process. Do you have any questions, or I will cancel the screen share?
Thank you, Tao.
Yeah.
I'll start with one question. With the second stage to go to 100% CO2 purity, you're looking at the alkaline sorbents. Is there is it also feasible to use physical sorbents, or is a chemical sorbent process necessary for the integration?
I think we prefer the chemical solvent because the concentration is still low. It's only 3 to 5%. For physical, the solvent, we generally employ it under concentration like higher than 30%.
Okay.
Yeah.
Yeah, I think we really need to look at the offshore humidity issues. And one of the advantages of offshore is that one of the reasons we're looking at there's a lot of reasons for offshore, but the fact that we have consistent high winds. So this is an off-the-wall question for Curran. Like, should we be thinking about having these systems at the hub level of turbines? That it might be an off-the-wall question, but it just seems like there could be some advantages there.
In terms of passing the air over the sorbents?
Yeah, and in terms of the humidity too. Both really have the data.
The solvent, like the higher velocity, if you have a higher wind velocity, it will benefit to the mass transfer. Yeah, but the higher humidity challenges the process, but it will just decrease the cyclic capacity of the solvent.
Does that
you have to cycle it more effectively?
Are you cycling it more but at a higher frequency, or will it lower your rate kind of per year that you're able to achieve as well?
Yeah, we will. The frequency of the operation will be the same. That's what we tested for both low and high relative humidity. We found that the cyclic time for one cycle is almost the same, but the capacity will be decreased.
And is your primary focus then more on kind of that greenhouse application for the kind of moderately concentrated piece, or are you equally focused on the pure CO2 part of the equation?
Currently we focused on the greenhouse because we just use the traditional moisture swing, and for a lot of application size, it's not very difficult to find like the heat or electricity, right?
Yeah.
Yeah, especially for the greenhouse. They said you only need water. That's great.
Yeah.
Yeah.
A little a background question on the lineage of the moisture swing. It seemed like you and time at Columbia, that was kind of the genesis of this moisture swing. Are there other people working in this that much, or?
Uh, uh, you know, Arizona University, because Klaus moved to Arizona University.
Yeah.
Yeah, and the professor from Carnegie Mellon is also working on the moisture swing process because they published a lot of papers on the moisture swing process. And there are another university in China, which is also working on the moisture swing process.
Okay.
And yeah, I think that's it. Not more, not much, not many.
Yeah. I know that Klaus is commercializing his technology at ASU with an Irish company, and their focus right now is really piloting, but their vision is really to create synthetic trees that are essentially distributed in a modular way all over the place. It's kind of the way he's described it. For the purpose of drawing down carbon. So there is, obviously a immediate commercial play in greenhouses, but there's, other pathways for it that are being thought about.
Sure. Yeah. I was just kind of a bit interested in the history as I was trying to read up on this, where all these things have come from, and he's working on what. So, yeah, okay. Well, that's quite useful.
We found that for the solvent, actually, now we are fabricating the solvent in China. As China has a lot of material candidates, and the price could be lower. And we found just several kind of powders material that is quite different from our previous material, so that it can decrease the half time from hours to less than 10 minutes. So that is the material development.
Yeah. In terms of the raw materials going into this, they're relatively available, right? There's not like rare earth things going in this or anything like that, right?
Pardon?
The underlying chemical materials going into making the device are relatively available, right? There's not some quite rare elements going in.
It is available easily, yeah, because this is a polymer. It could be it's used. Yeah, I just showed the functional group is it's just normal. Yeah, you can see that. Yeah,
that's what I thought. I just wanted to,
it's a polymer.
confirm.
Yes.
And that was one of the things that attracted us, for our open source project, is not only the modularity of it, but that the inputs for the sorbent were pretty off the shelf. It sort of promotes the idea of universal tinkering. But some of the things that Tao just described, and a whole host of other issues that his lab and researchers are working on, that's kind of the reason why we're starting this open source project, is to create a miniature unit that would allow us to attract communities of people to focus on some of these key problems, and hopefully use a crowd to advance Tao's technology with his leadership. So would love to keep you posted on that. You're invited to certainly come in and participate on that as we move forward.
For sure. And one other question just was around, so you talk about functional groups are relatively well bonded.
I might just build one at home.
Exactly.
What would the degradation mechanism be? Like, what would we expect in terms of longevity of the actual solid sorbent piece?
You ask the degradation mechanism of our material or the amine.
Your material.
Oh, um, I think it's the degradation first is quite weak. Yeah, because the material was tested for over 20 years, and the degradation reason maybe is from the functional group because it's linked. It's a quaternary ammonium cation, and it is linked to the backbone of the polymer. So it may be because you can smell some of the amine, yeah, amines from the material. So clouds think that is kind of a degradation, but actually, if you measure the capacity, it is very stable, yeah, in years, yeah,
Okay.
yeah.
Yeah.
And of
Great.
course, you cannot use the material at a very high temperature, like over 80 degree, over 80 degree, or 80, yeah, 80 to 100 degree, the material will be degraded. But under normal temperature, it is quite good.
Yeah. Yeah. Okay.
Yeah.
Makes sense. Okay. Well, that's certainly helpful to figure out how it's actually working, and the trade-offs, pros, cons, all that kind of stuff is great to hear right from you. So I really appreciate your time there.
Definitely, and certainly.
Sorry,
You're now.
I didn't hear very well because of my. Oh. Sorry, I think my connection is quite poor. I didn't hear 100%, but if I understood correctly, there's no particular attrition of the sorbent that you expect. Does that change in for instance, a kind of a more of a marine environment where the ambient humidity, is going to have, entrained droplets of water with salt in it? Is that going to be something that risks poisoning the active sites?
Yes, because we said, you see, the material is a kind of ion exchange material. So if the environment has some ions like chloride, salt, because most of the salt has chloride. So if you have a lot of chloride surrounded, and the functional group may be exchanged by the chloride because it was alkaline, and then the alkaline groups was exchanged by the chloride ions, and then the capacity will be decreased. But it can be recovered very easily because, for example, if you used for several months, and it's a lot of functional group was exchanged by the chloride, and then you can wash it, but you can put it back into the alkaline solutions and exchange the the chloride out. Yeah, so it can be easily regenerated by alkaline wash.
Got it. And that leads to, I guess, a follow-up question that I have is that with the systems involving ion exchange resins, you often have this alkaline wash. Is that does that amount to a significant material input to the overall process? Or is it a sufficiently small rate of, say, sodium hydroxide consumption that it's not going to be an impact with respect to life cycle considerations?
In the normal atmosphere, generally you needn't to do the alkaline wash. Maybe you need the alkaline wash every 3 or 5 years. But I'm not sure for the salty atmosphere because we seldom tested in the atmosphere. But I can imagine that the ion exchange because of the concentration difference. If the chloride concentration is higher than the carbonate, then it will exchange. And I just can guess that the chloride in the air is not that high. Or compared to the the alkaline groups in the solvent, it is quite low. So the ion exchange process will be very slow. Maybe we will do the alkaline wash once a year or twice a year. It's like that. Yeah, I don't think it will result in very frequent alkaline wash. And by the way, you can easily deal with the alkaline, right? It's not that harmful. Yeah, it's just a kind of alkaline solutions. Yeah, like sodium hydroxide. Yeah, you can even use that.
Yep. Okay. Thank you.
Yeah.
Great. Well, thanks, Tao. I'm wondering if we could do this a little backwards.